Okay, so we're going to talk about temperature conversions today. You will not get a worksheet with temperature conversions. I really just want you to kind of understand the scale or how you equate Celsius and Fahrenheit. The first one that we'll do the most often in here is this, oops, got it right in the right color, is the Kelvin to Celsius conversion. Okay, that's the easiest thing we'll do in here. It's add 273 to your Celsius temperature. If you're going from Kelvin to Celsius, you do what? Minus 273. So that's definitely the one we use the most often. But I do want us to track just a couple just so you can kind of see how they relate to each other. Note that when we have the Kelvin temperature, it does not have a degree sign. It's just Kelvin. Whereas the Celsius and the Fahrenheit are degrees. Fahrenheit or degrees Celsius. Kelvin is actually just Kelvin. Okay? So here is just kind of a visual for you to kind of understand and see what their temperatures are at the different points. Water freezes at 32 degrees Fahrenheit, which is what we're used to using in the United States, which is the equivalent of 0 degrees Celsius or 273 Kelvin. Water boils at 212 Fahrenheit, 100 degrees Celsius, and 373 Kelvin. So as you can see, when you're looking at the Fahrenheit to Celsius, you can't just think, oh, it's 32 more, because that's what it is at freezing, because at boiling, it's 112 degrees difference. So it's because of that formula. So we're going to do two of these conversions together. Y'all are going to actually just tell me what to write. I'm going to write it, and we're going to calculate it. Okay? So we're going to do number 1, 263 Kelvin to Fahrenheit. So what is the first step I need to take? Get it to Celsius, correct. So I'm going to take 263 minus 273, and that will give me a negative 10 degrees Celsius. So how would I convert negative 10 degrees Celsius to Fahrenheit? So what is the...
Add 32. Multiply by 1.8 and add it by 32.
So I'm going to multiply times 1.8, and then I'm going to add 32 to that. So that's going to give me what in Fahrenheit? A 14, correct? All right. That is cold. That is very cold. Okay. Now let's do 13 degrees Fahrenheit to Celsius. It's going to be around in the 10, negative 10, right? Because not that much, but let's see what it is. So in this case, what do I do? Now I subtract 32. Then divide by 1.8, and it should be negative 10.5 degrees Celsius. And then just for grins, number 4 should be very easy. You don't even need a calculator for it. 25 plus 273 is 298 Kelvin. Okay? All right, any questions on that? I don't think so. Well, the 273, yes. I mean, we'll use that all year. I mean, I show you so you can kind of understand because, I mean, like in other countries, everybody's already used to dealing with things in Celsius, so they kind of know. But for us, if I say something's 25 degrees Celsius, if you're not used to thinking in Celsius, you'll think that that is actually cold, but it's room temperature. That's what, which is about 75-ish, somewhere around there. So it's just to get us thinking in the proper terms, because that's actually considered to be a standard condition is 25 degrees Celsius, which is room temperature. But if I just said 25 degrees, y'all are going to think, obviously, Fahrenheit, like, oh, it's wintertime. We get our one day of cold weather in Texas. Yeah. All right, so let's talk about derived units. Last week we talked about the base units. The SI units for time was seconds, and length was meters, and mass was kilograms. Today we're going to talk about derived units. So they're not actually SI base unit, but they're units that we derive to get them. Yes, ma'am?
When calculating a change in temperature, why will it not matter if the change is recorded in Celsius or Kelvin?
Well, why wouldn't it?
I actually just added.
Huh?
She read the discuss question of,
Okay.
before.
So why do you think it wouldn't matter? Yeah.
It's just adding.
You're just adding 273.
So then it doesn't matter if it's in Fahrenheit.
No, it doesn't say Fahrenheit, does it?
Well, yeah, but then you could just change it to Fahrenheit.
I know, but that takes multiplication.
But that's a different scale, and so we're doing one we're multiplying and dividing, so that changes it. If we're talking about Celsius and Kelvin, their only difference is adding or subtracting 273, so it's a standard, the same both directions basically. So the delta T, or your change in temperature, doesn't matter if you record it in Celsius or in Kelvin. It does matter if you.
Oh, because it's an amount.
Yeah.
Yeah, I didn't realize that.
Well, that's okay. All right. You good now?
Yeah.
Awesome. I forgot that was on there. I meant to discuss that and I forgot. Thank you for reminding me. Maybe it's lack of oxygen to the brain. No, just kidding. It's like I can't get a deep breath. Okay, so derived units are just taking those units that are base units and making them into other things. For instance, volume. How do we measure the volume of a solid? Length times width times height. Okay, but aren't those all basically length, just different directions? Okay, and so for volume, we could take meter times a meter times a meter, and it'd be meters cubed. Okay, and then that's how we get volume. So for us, we're going to tend to use milliliters. Okay, so you do need to memorize this, that right here. 1 milliliter, you don't have to do all the little zeros, is equal to 1 centimeter cubed. Okay, centimeter cubed is what we tend to use for a solid. Milliliter is what we tend to use for a liquid. Like if you go to the store and you buy a 2-liter bottle of Coke, that's a volume, which would be the equivalent of 2,000 milliliters. Okay. So how many of you have ever watched any kind of medical drama? Grey's Anatomy, whatever. And someone's in the emergency room and they always say, give them 15 cc's of whatever, blah, blah, blah. Cc's is the same thing as a cubic centimeter, which is equal to that. You don't have to memorize that. I just thought you'd like to know that because you watch those shows and they're always talking about cc's. It's the same thing as a milliliter. cc stands for cubic centimeter, right there. Okay.
Same thing as a milliliter.
Which is equivalent to a milliliter, yes. They just say cc's. I don't know why. That's just what they do. But I just thought you'd like to know that. That's like extra information I'm not going to even charge you for. I'm sorry, what?
Because ml is 2. I guess so.
Yeah, I guess so.
It's the same, like,
Huh?
syllable.
Cubic centimeters is really long.
Well, cubic centimeters is, yeah, cubic centimeters is long to say, so they shorten it to cc. But it's the equivalent of a milliliter.
What if you mishear somebody?
Okay. The next derived unit that we're going to talk about is density. Okay? Density is equal to m over v. It's your formula, which stands for mass over volume. When we're measuring density, if we're measuring it for a solid, we tend to do grams per centimeter cubed. For a liquid, we tend to do grams per milliliter. And for gases, we do grams per liter. Okay? Because gases have a very low density, so if we were to do it in grams per milliliter, it'd be a really, really small number. Okay? I think it says somewhere on your paper that the density of water is 1.0 grams per milliliter. Memorize that.
It just says 1 gram.
Oh, 1.0. I'm just being extra precise today. What that means is 1 gram is equal to 1 milliliter. So if I were to go in the lab and I would pour out into my graduated cylinder 75 milliliters, how much would that have? It would have a mass of 75 grams. Okay. There's the rain. Okay. Even if this is how I know who my band kids are when it rains and they're cheering.
Except for all the extras are going to be gone, and it's really
Oh, yes!
Okay.
Just have to take a bunch of time to just like remark and I want to do that.
All right, so when we're talking about density, let's bring it back in. I know you're excited about the rain, but I am recording.
Oh.
Yeah. Okay, when we're talking about density, we're talking about basically a concentration of matter. Okay, so the more concentrated or the more dense, you're going to have more particles per the same amount of space. So this is not a trick question. Which box has the most density? The first one, right? This one.
Yeah, circle it.
Circle. Whoops.
Ooh.
Are we
Oh,
supposed
oh,
to write
Oh,
this
same
down?
volume.
There. Same volume, but cube 1 definitely has more particles, so it would be more dense. So it's like that question I asked y'all back in the very beginning of school. If I had a pound of feathers and I had a pound of gold, which one would have more volume? The feathers would have more volume
Take up a lot.
because gold is very dense. So it's
chunky.
this a pound of it's not going to take up a lot of volume, but feathers are very not dense, and so it would take a lot more volume. Okay. To equal a pound. So that's how you can think of concentration of matter. Think of gold and feathers.
Gathers.
Gold feathers.
Golden feather.
It's gathers.
Yeah. Okay. So we're going to be using density as a conversion factor, but you do remember I told you you need to memorize that density is 1 gram per milliliter. Okay. So the way you decide if something is going to sink or float is you calculate its density and see is it greater than 1 or less than 1. In this case, vegetable oil is less than 1, so it floats, which is why when there's oil spills in the ocean, the oil stays on top because it's less dense, so it floats on top. And the oil and water don't mix.
Yeah.
That's another lesson, another day.
Like,
It'll float.
It has to do with their bonding, that type of bonds they have.
Yeah, well, if they throw a head of lettuce in the ocean,
I don't know what the density of a head of lettuce is.
well, vegetable oil, it might as well be the same thing.
No, not the same thing. No.
It's a vegetable.
Okay, so this process is going to be an important concept because we are doing a lab on Friday of density, okay? And we're going to be measuring the density of some unknown metals. And this is the method we're going to use. It's called water displacement. So what water displacement is, yeah, because if I have a volume of water and I drop something in there that sinks, what's going to happen to my water?
It's going to go up.
And the amount that it goes up by is the volume of the object.
Yes.
Makes sense, right? Pretty simple. Okay. So we're going to do an example so you can at least have done one calculation for the lab because that's going to be Friday. Or it'll be Monday. So we have an unknown metal, has its mass. Originally the graduated cylinder had 31.47 milliliters of water. After we added the metal, it rose to 58.85. Calculate the density. So first thing we need to do is get the volume, right?
Yes.
So we're going to do 58.85 minus 31.47.
And then you get 27.38.
27.38 milliliters.
Oh, sorry. It said grams, so I guessed.
Is it 27.38?
Yes.
Okay. And then now we just do density is equal to mass over volume. So it gave us in the problem 287.8 grams divided by 27.38 milliliters. And what does that number come out to be?
10.51132211.
Uh-huh.
wow.
Now, we said grams per milliliters, but we know that this is a solid, so technically it would be more correct to change that to centimeters cubed because we are dealing with a solid. If you didn't, it would be okay. I wouldn't,
Why would it not be milliliters cubed? Or liters cubed for gases and liquids?
Because it's more spacious.
Why would it not be liters cubed?
Or like, so at the top where it says solids or grams per centimeters cubed, why isn't it liquids grams per milliliters?
Oh, because a centimeter cubed is a milliliter. It's defined as that. So a milliliter is equal to a centimeter cubed. Does that make sense? Yeah. And then milliliter and liter is just different prefixes in front. Yeah. Because we're not measuring like for centimeter cubes, it's assuming you measured length times width times height.
So assuming.
Yeah, it is the milliliter is equivalent to a centimeter cubed. Okay? All right, so let's do a couple of practice ones, and then we're going to stop for the day. Well, I'm going to stop for the day. You're going to work on your worksheet, which is due tomorrow, by the way. Okay? The density, that is a typo. There's no way that the density of mercury would be 13.6 grams per liter. So that's supposed to be, well, it's actually supposed to be, it should be milliliters or centimeter cube. But to make it our life easier, let's just put that as milliliters. Okay? Yeah, otherwise it would not. That's way wrong. because in terms of liters, that would be a heck of a lot higher than that, okay? It says, how many grams would 1 liter of mercury weigh? So we're going to start with 1.00 liter. And we're going to say in 1 liter are 1,000 milliliters. And then we have 13.6 grams per milliliter. So a liter of mercury would weigh 13,600 grams. Is that what y'all get? So we just used density as a conversion factor. That's all we did. We just said, hey, if 1 milliliter is 13.6 grams, how much would a whole liter be? Okay? Make sense? Okay. The next one says a solid has these dimensions and a mass of 28 grams. Will this solid float in water? So we just have to see what is its density. Is it greater or less than 1? So we're going to do volume is 3 times 4 times 2, 24 cubic centimeters. And then density is 28 grams divided by 24 centimeter cubed. Excuse me. 1.16, something like that. So it would sink.
On the test tool, we have to have all of these conversion factors memorized.
You do have to have water.
But like, that 1,000 milliliters equals 1.
Oh yeah, you have to know that.
We do have to know.
You have to know those prefixes. Remember, when I showed you those prefixes, I drew lines to the ones you have to memorize. Yeah, absolutely, you have to have those memorized. Now, things like pico, mega, things like that, we won't use very often. Well, most likely they're not on the test, but if they were, I would give those to you. But not their standard kilo, milli, centi, deci. I wouldn't give you those. You have to know those. And those are the ones we use the most often. Nano is, yeah. 1 to the 9. It's easy to remember. N and N. 9 nano. Nano 9. That's how I remember it. Gas has a density of 0.824 grams per liter. That is an appropriate number for grams per liter, and it's a gas. Occupies a volume of 3 liters. How much does it weigh? So 3.00 liters, right? 0.824 grams per liter. Cancel, cancel. Comes out. You can let me finish, and then I know what you were going to ask. What does that come out to be?
2.47.
2.47. We're going to go with that. Grams per liter. You were going to ask, couldn't I just use the D equals M over V and substitute? Yeah, but isn't that what I did?
Yeah, but I just didn't.
Yeah. So the thing about that, and that's a good question. She asked me on that last one, why couldn't I have just done D equals M over V and solved for mass? But if I rearrange that equation to solve for mass, what am I taking? Density times volume, which is what I did right there. But that just kind of shows you how dimensional analysis, you don't even have to know the formula. You can just do it to get your units to cancel, and you don't have to know the formula. Now, we happen to know the density formula because it's easy. But like if you go on to, say, physics, or when we're doing the gas laws, if you can't quite remember the formula, but you can get your units to line up, you can solve for anything. Anything. Especially when you get to physics and you get all those formulas in physics. And you're like, oh, what was the formula for work? I don't remember. Well, if you got your units to cancel, then you're good. You're golden. It's a very powerful tool in science class for the math. Maybe not biology so much, but there's not much math in biology, right? Okay. That is the end of the lesson today.